This air compressor consists of an electric motor that compresses air into a storage tank. The compressed air can be released at chosen pressure when required. How works an air compressor? What are the criteria for selecting a proper air compressor? Well, there exists a variety of different compressor types. Let's continue with an overview. Normally, the compressors used in the field of automation and workshops are the so-called positive displacement compressors. Here, pressure is excited when air is drawn in a chamber and the volume of this chamber is reduced. In this video, we want to confine ourselves to this type of compressors. Let's have a closer look at the reciprocating compressor. As the crankshaft turns, a piston reciprocates within the cylindrical housing. The inlet valve, also called suction valve, allows atmospheric air to enter the cylinder. This is done during a suction stroke of the cylinder. The outlet or discharge valve opens at high pressure during the compression strike. Air heats up when it is compressed. This is a problem of each compressor. The result is not only a less efficient compression cycle, but also to a real danger of explosion if any inflammatory substances, such as oil or lubricant, get contact with the overheated air and piston. Therefore, the compression of a single-stage compressor is limited to an output pressure of about 10 bars, or 145 psi. To achieve higher pressures, you would use a multi-step compressor. Here, a two-stage compressor is shown. The large piston builds the first stage. The air leaving the first stage can now be cooled before it enters into the second stage. With a two-stage compressor, you achieve pressures over 20 bars or 290 psi. Multi-stage compressors with high power also can use water cooling to avoid overheating. Based on its working principle, the reciprocating compressor delivers only pulsed compressed air. Therefore, this type of compressor is used in conjunction with a tank. However, the use of a tank offers the advantage that the compressor can be operated with a two-point controller, resulting in less energy consumption and wear. The diaphragm compressor belongs to the family of the piston compressors. Here, the suction chamber is sealed from the piston by a diaphragm. As an advantage, the compressed air in the compression chamber does not come in contact with the lubricated piston, and thus can be kept free of oil. The weak point of a diaphragm compressor, in general, is its membrane itself, since the elasticity is limited. You would use the diaphragm compressor, for example, in the food industry or to fill divers' bottles. A totally different working principle has the so-called rotary compressor, also named as vane compressor. The typical rotary compressor has a cylindrical housing. Adjustable rotary vanes with its center point on an offset drive shaft have contact with the housing. So when the shaft rotates, these vanes create chamber of variable sizes. Air is sucked into the largest chamber, being compressed, and leaves the compressor at the smallest chamber. Advantage here is in the pulsation-free flow, in contrast to piston compressors. Therefore, an air tank may be optional. In addition, these compressors are quiet and relatively insensitive to dirt. Typical applications are, for example, wastewater treatment, fish breeding aeration, dust collection, vacuum packing, and so on. Watch also our next videos.
At Doosan, we're always viewing the world in unique ways. For example, did you know the Earth processes air much like a compressor? The weight of our atmosphere actually compresses air, generating 14.7 pounds of pressure per square inch at sea level. An air compressor processes that same air we breathe to store energy and adapt it for use in countless applications. Let's look inside a typical unit. Ambient air enters a compressor through a filtered intake which removes dust and dirt. This filter should be replaced at timely intervals to ensure the compressor is protected from unwanted contaminants. Dirty or restricted filters cause pressure drops and reduced efficiency. Filtered air continues through sealed piping to an inlet valve that controls the volume of air reaching the air end and prevents oil from reversing towards filters after shutdown. Next, air enters the air end, which is a fixed displacement pump that uses two helical rotors to compress air. As the rotor screws turn, they form a partial vacuum which sucks air into the helical rotors. The amount of air that fills the air end is measured in cubic feet or meters per minute. As air travels along the helical rotor flutes, the space storing the air gets progressively smaller. Since the air cavity between the rotors is larger at the inlet end and smaller at the discharge end, air becomes compressed, creating significant heat. During the process, oil is injected into the rotors and serves three critical purposes. 1. To lubricate the rotors, bearings, and seals. 2. Seal the space between rotors to keep pressurized air from escaping back to the inlet. And 3. Remove heat from the system so the air end can run at optimal temperatures. Using oil to maintain proper temperatures maximizes efficiency of the compression cycle. The air, now mixed with oil, exits the air end through a discharge port and is piped to a separator tank. Here, the separator will remove some of the oil from the air and let it accumulate in the pressurized tank. The tank acts as a reservoir as well as an oil service and fill point for maintenance. A sight gauge mounted on the tank's side allows an operator to quickly check the oil level. Next, hot oil flows from the bottom of the separator tank and through the oil temperature bypass valve. If the oil is too hot, it moves through a cooler to lower the temperature. The oil temperature bypass valve also acts as a mixing valve, taking hot oil from the separator tank and cooled oil from the cooler and mixing them into a perfect temperature for the air end. The oil is then filtered and returned to the air end, ready to do its job all over again. Back at the separator tank, the air is almost ready for use. Air exits the pressurized tank and passes through an element filter which reclaims most of the remaining oil from the airstream. The air is then piped out of the compressor to the service air valves where it can be used for thousands of applications.
The conveyor belt is driven by three-phase AC motors. How is it possible that this line can start and stop so smoothly? Let's have a look at the control. It's all because of the frequency inverter. Other common terms for this electronic device used in drive technology are VFD, known as Variable Frequency Drive, Adjustable Frequency Drive, or AC Drive Converter. With this device, you can control speed, torque, and direction of an AC motor at the same time. So let's know this device better. This block diagram illustrates a typical three-phase AC variable speed drive system with its main components. First, the incoming AC voltage enters a bridge rectifier, which consists here of 6 diodes. In this stage, the DC voltage has ripples. Therefore, a capacitor and a filter helps to smooth out the ripples. Now, the DC bus system can take its place. The filtered DC bus voltage passes through to a DC three-phase AC converter. The DC AC converter consists of an array of fast-acting switches which convert the DC voltage into voltage pulses of square shape, constant magnitude with varying width. The inverter output is not a truth sine wave, but an approximation based on PWM or pulse width modulation. This pulse width modulation scheme works because the motor coils are large inductors, which does not allow current to pulse like the voltage. To ensure the efficient operation of the motor, the sine waves produced by each pair of inverted switches are 120 degrees out of phase. The longer the switches are on, the higher the output voltage. This way, you can control the torque of this motor. Regarding the speed of the motor, by increasing the frequency of the output signal, you get a higher number of revolutions. But now you have a problem. The inductive reactance of the motor coils rises by the signal frequency. That means you would get less torque. So, what is the solution? To overcome this obstacle, you would adapt the voltage to the frequency when acceleration and deceleration. The parameter called ramp describes the voltage-frequency ratio. The other parameter, boost, also known as the torque compensation, is to compensate the torque decrease in low speed because of the stator winding resistance of the electric motor and the starting torque caused by friction. The base or edge frequency is achieved when the voltage supplied to the motor reaches the mains supply voltage. Raising the frequency above the edge frequency leads to magnetic saturation, which cannot be compensated anymore. As a result, the torque of the motor decreases. Concerning the technical implication of the inverter, as electronic switches, transistors are used, in this case, IGBTs. In order to avoid a short circuit, their control connections are interlocked. The diode serves as a freewheeling diode, since the motor coil is an inductance.